This is Russ Wilcutt, Associate Editor of Modern Machine Shop Magazine. Welcome to How to Achieve Maximum Results to Become More Competitive in Grinding for the Mold Industry, which is being presented by members of the United Grinding Cylindrical Group. Thanks for joining us. Forecasts show that the mold industry will be one of the top spending industries. The United Grinding Cylindrical Group is holding this webinar to help you capitalize on this forecast. Hans Yulchi will brief you on questions the industry has while providing examples of how to improve the processing of parts in the mold shops. Doug Emerson takes a deep dive into increasing your competitive edge. He will show operation plans and best practices for OD grinding applications. Andrew Osborn will focus on the applications that require ID grinding. Andrew will provide you with the technical content to take the next step in adding mold grinding to your business. Tom Vieira, Cylindrical Applications Manager, will be joining the panel for the Q&A segment. So thanks again for joining us while we go from a high-level view to the most intricate details of becoming successful in grinding for the mold industry. Topics will include components of grinding in the mold industry, sample operation plans in the mold industry, how to OD grind in the mold industry, and how to ID grind in the mold industry. As for our presenters, Hans Yulchi has 37 years of experience in grinding applications, sales, process engineering, and grinding system integration. As Vice President of the Cylindrical Division of United Grinding North America, he is responsible for sales and applications of Studer, Shout, Microsa. Doug Emerson is Regional Sales Manager at UGA and has 30 years of grinding experience in the areas of sales, application, and service. He has worked with many mold companies providing grinding solutions. Andrew Osborn, the project engineer for internal grinding, has been in the grinding industry for 3 years, specializing in complex internal forms with fine surface finishes. The presentation will be followed by a Q&A session. It's easy to submit questions, and I encourage you to do so during the presentation. Simply type your question into the question pane to the right of your screen. We'll do our best to get to all of them, or you can contact our panelists directly afterwards. With that said, let's get started.
Okay, good afternoon, and thank you for joining us for this webinar. Many mold manufacturers have these questions. How do we become more competitive? How do we compete with low-cost producers of these other regions? How do we produce better quality? How can we deliver faster to our customers? How can we get more out of less trained operators? How do we produce better results? Well, these are a lot of questions. So during this webinar session, we'll try to address some of these questions that come from the mold manufacturing industry. This webinar concentrates on cylindrical grinding of mold components, even though our company has been involved in other areas that include surface grinding applications of high-precision mold components. Mold work is, as many realize, very challenging and can put a lot of demands on grinding machines and its operators. In addition to being difficult to hold clamp the work pieces in various stages of machining, over the years we have solved such challenges by developing specific clamping and processing methods. Grinding and grinding/hot turning combination machines equipped as basic single tool up to multi-tool stations or turrets can help solve such challenges of concentricity and can bring a reduction of the number of setups. What this can mean is to do a roughing process and finish grinding in the same setup, or it can, as an example, also include turning or grinding of a thread. So here's something about confidentiality. We adhere to confidentiality of individual customers and processes. So by this, we have to be very careful not to show certain key information in this presentation, and we'll only talk about potential setups and applications. In case you feel that you would need more specific answers not addressed in this webinar, or due to confidentiality are not able to ask, we can certainly set up an NDA, and you can then request information regarding your specific case individually. So in regards to the agenda topics here, items to consider when you look at the mold making grinding machine. So the first one will be smart software, machine technology. How is the machine equipped, or how should it be equipped? Automation. How does that play into the role? Measuring systems. And then we go into the overview of applications and into the setup of specific products and applications. And then also we will talk about potential applications available. In the end, we'll make time for questions and answers, and Tom Vieira will join us to answer questions from the application side. So, what should you consider when you're looking at grinding of mold parts? Well, what if the operator doesn't have the grinding experience? What do? What feeds and speed should he use? Well, what kind of grinding mill should he choose? Should he go slow first and make sure it works? Well, smart grinding software of today may be able to show you how to grind a part. The software may be able to get the part right the first time. The part can be ground faster. The software may be able to remove your gas factor. Smart software, what does it do? Technology software will always get you close to where you need to be. It is just like a GPS. As it provides you with a plan on how to get somewhere and how long it's going to take. Technology software has built-in knowledge base or a built-in knowledge base. This is why it's smart. Technology software can predict the grinding time. Technology software can check your collision problems. So in other words, you know ahead of time where you may have collision issues. In regards to dressing, items to consider. It can help you dress the wheel profiles fast. Look at the time benefit factors in this chart. In some cases, this factor is up to 15, so you can produce the part or dress the wheel 15 times faster than conventional CNC dressing programs. Or it can help you to copy and paste the profiles from the parts to the wheel. It can make the process more visible for the operator. It can bring confidence to the operator. So the cost benefits are check process capability, short changeover time due to virtual setups of the machine. So in other words, the machine can be set up on a laptop or on a PC up front without moving things on the machine, without disrupting the previous grinding application. A fast way to get optimized the process. The shorter cycle times, which means more available machine capacity. Or it can reduce the reduction of errors and obviously cost due to the fact that we can simulate. So in regards to quality benefits, the process becomes reproducible. They can be standardized, so the documentation is the same each time. Quality is not dependent on the operator. Consistent processes, that means over and over, the process is the same. Okay, let's go to how a machine like that can be configured. This is what we would recommend for you to look at. First of all, it needs to have a thermally stable base. This will allow for consistent size throughout the day, independent of changing of temperatures. The dampening capability. You should look at a way to dampen the process. This will give you a better surface finish. Precision guideways and drives. This would help to make the part straight and allow you to do better path control movements or for fine and smooth areas, and interpolation in particular. Full B-axis capability or infinite B-axis capability. This would allow you to produce tapers much more easier and become much more flexible with grinding wheels. Acoustic monitoring. This would allow for process and dressing, for grinding process and dressing process, monitoring and fine-tuning the process, as well as speed up the setup. Besides that, it would be can be used, as, of course, as a gap control. Automatic precision balancing. So this will improve the roundness and the surface finish. Measuring feedback capability. The measuring feedback capability will allow to audit or to check parts for quality and could allow for closed loop feedback control. Talk a little bit about automation. Under automation, we see people that simple use of a simple automation to bridge time. Simple automation would allow the operator to tend the cell with more than one machine. Simple automation would improve loading consistency, especially in grinding. This is very important for parts that are loaded in chucks. Simple automation can be run via the grinder control, so it keeps the setups very simple. Okay, let's talk about measuring. There's various possibilities. One of them is in-process gauging. In-process gauging or measuring is typically used for higher volume, high precision applications. External post-process audit. So this will be where, independent of the machine, the parts will be measured each time or after a few parts are done. And then you will want to look at post-process with feedback. So in this case, the machine is controlled via a feedback and creating a closed loop control. This would allow the automation or the post-process to adjust the machine if it changes over during the day or during the process. Machine internal post-process would be similar, however, the measuring would take place in the machine while the part is still clamped. In this case, there will be additional cycle time due to the measuring cycle. However, the part would not be unclamped and would be measured in the clamped status, which sometimes is also better. There's another measuring called machine internal intermediate process. So that means the part would be measured in between cycles and would allow for the machine, for this part to be measured before it's finished and potentially adjust of the size before final size is reached. So these are some of the things to consider to be more competitive when you're looking at a CNC machine to grind parts in the mold industry. So this portion, this will conclude my portion of the presentation, and I will hand over the microphone now to Doug Emerson.
Thank you, Harald. There are several components which require grinding in the mold industry. For this presentation, we're going to concentrate on parts for the actual mold components as opposed to components that would be integral to a mold-making machine. The series of applications we will discuss are components for PET containers, core pins, lighters, and other typical parts used in molds. Of course, there are several more applications, such as pharmaceutical containers, cosmetic containers, medical components, personal care, caps and closures, food and beverage, to name a few. In fact, more than likely, within arm's length of you right now, there's something that was produced by a molding process. First, let's look at a core pin, which is used to manufacture PET bottles. In our case, this is machined on the S242, a combination grinding, hard-turning machine. The workpiece is installed on injection molding machines and is designed for shaping the PET bottle blanks. These so-called preforms, which you can see at the top right, are the raw parts for a PET bottle like those we use every day. In fact, if we look at a few numbers, PET bottles are in more demand than ever, and studies show this demand will double in the next 15 years. In the United States, approximately 50 billion bottles of water are consumed every year. That breaks down to 15,000 every second. These figures show a huge potential in this industry for not only the core pins, but other mating components used in the molding of PET bottles. Let's take a look at a possible processing solution. In this example, the workpiece core manufacturing is divided into two setups on the S242. We will concentrate on setup 1 for today. As for information in setup 2, the pin's false center is cut off and the workpiece end radius is hard turned and ground, supported by a steady rest. The demand on the PET industry is to launch bottles with ever-increasing thinner walls. This reduces shipping costs of the end product for the beverage producers. This, however, greatly increases the requirements regarding the concentricity of the individual workpiece diameters. We can meet these requirements through a combination of turning and grinding in a single clamping. We start with the turning operation, where the left side of the part is turned to the finished dimensions. The diameters and shoulders to be ground on the right side are pre-machined with optimal allowance to minimize the grinding cost and time. Requested geometric modifications of the PET bottle blanks can easily be reprogrammed. This offers a very high flexibility for core producers to make several different part families. Dimension is checked post-process with the machine's measuring probe. Any turning tool wear can be compensated with this process. The next operation is the grinding. First, the diameters and shoulders on the tailstock side are ground. You can see the grinding wheel is dressed with a profile. This is so different sections of the wheels can be used for the various grinding operations. Next, the taper is ground as the final operation. The required lengths and diameters are controlled with specially designed in-process measuring head. Note that the shoulder height in this example was approximately 0.2 millimeters. This represents an additional hurdle with the gauging design. In order to protect this precise measuring heads from chips during turning, they're completely covered. You can see that image on the left. The cover is only open for the grinding operation with the gauge slide ready for the approach on the workpiece. In setup 1, we'll talk about the clamping device here. In setup 1, the workpiece is clamped between centers. The 3-jaw chuck is equipped with a center point as a workpiece stop. The jaws remain open and were used for driving the driver plate. The driver plate, you can see, is screwed into the jaws. The jaws only come into play during operation number 2. Here the workpiece is clamped on the diameter and additionally supported with a steady rest. Thanks to this tooling design, the customer can cut down on the changeover times. We can now take a look at the cycle. The cycle starts with a positioning cycle to establish the lateral tolerance for position. This compensates for any center hole variance from part to part. As the turning starts here, in this particular example, I wanted to point out that we are driving the component with a synchronized tailstock. This allows us to use no special clamping device at all. Also, I want to note this example is not showing the specialized gauging for the in-process measuring we discussed. The tailstock rotates at the same RPM as the workhead, which allows us to turn the part between centers using only minimum pressure and eliminating the need for special work holding. Also, the tailstock moves on its own axis, so the distance between centers and clamping pressures are programmable. This would reduce changeover times from part to part families. This particular model machine has 3 center distances from 400 to 1,000 millimeters, depending on the amount of cross slides it is configured with. You can also see the 45-degree incline of the machining bed ensures optimal chip flow from the machining area and good access to the work area. The granitan-based material also provides excellent vibration dampening for maximum thermal stability. Right now, you can see the probe going in, measuring and compensating for the wear from the turning tool. Now the second position is coming on with the grinding wheel. This will start the grinding of the workpiece. One thing I'll note is this particular machine in the video is processing the part with 2 cross slides, but a third is possible. The cross slides can be an external grinding head, either straight or angled, a turret with a fixed or powered tools, or an internal grinding head which can accommodate 3 different high-frequency ID spindles. As we're grinding the tailstock side now, the next operation will be to index over and finish grind the taper. Okay. Cycle complete. The above chart represents what a standard process could be for such a component with traditional operations. This particular case was 6 operations totaling 14 minutes of cycle time. This includes 6 setups and 8 days of idle work in process time moving from operation to operation. As you can see, the cost savings potential now for producing such a part in a combination process machine for a lean manufacturing method. Here's an example of producing another core pin for much smaller parts than we previously discussed. We're going to look at 2 different ways to process this and the pros and cons of each. Several factors will determine which method is best, such as overall volume, lot sizes, and tooling requirements. The first method will be contour grinding with multiple wheel approach. Second would be plunge grinding with profiled wheels. Example 1 is the contour grinding. The part is first rough ground using a CBN with contour grinding cycles. Then the machine is set up with multiple conventional wheels for finishing operations. The advantage for this method is flexibility. This would be suitable in the case for running a multiple parts family. Setup from part to part is very short. In fact, it could just be a matter of seconds if calling up the next part program is the only requirement. The worst case would be adding a steady rust adjustment. The disadvantage would be longer cycle times. After contour grinding the right side, the taper is ground automatically by indexing the B-axis to the appropriate taper. The taper angle can be programmed to within 1/10,000th of a degree. Here, a second profile wheel will be indexed into position to grind the grooves. This could be the same setup or a separate setup depending on the number of available spindles on the machine. Because of the fragile nature of the part, it is not squeezed between centers with a tailstock, but pulled back into the workhead center using the string method. And the tailstock is only lightly supporting the end. Here, in this example, instead of roughing with the CBN, this is example 2, by the way, we are roughing process with 2 profiled dressed grinding wheels. This will produce parts much faster and allow for more dedicated work holding. However, it will be less flexible than example 1 and require the wheel changes for a family parts where characteristics change. We first rough grind with the contour dress wheel. Then we index the wheel 2 and rough the left-hand section of the part. Then in finishing, the left-hand section with a profile wheel is finished ground. Finally, we finish the right-hand side again with a profiled wheel. Depending on the number of machine spindle configuration, this could be done in either 1 or 2 cycles depending on the number of spindles. With either example 1 or example 2, the task can be done. Again, the production requirements will dictate the best method for each individual case. I'll hand it over to Andrew Osborn now.
Thanks, Doug. The mold body for a standard lighter is another part that's typically ground on a cylindrical grinding machine. This requires the rotation of the part to coincide with the movement of the grinding wheel. Grinding a non-round part such as this provides some additional challenges. Some of those challenges include the force orientation and the wheel size, which is dictated by the geometry of your part. On this part, there are multiple setups that require you to grind, multiple setups to grind the lighter mold. The first setup is to grind the round diameter so that they can be used for clamping in the following operations. A two-jaw chuck and a center are used to clamp and locate the part for the starting operations. After the round features are ground, the part is flipped for grinding the outer round feature. In order to properly align the lighter body form, a flat on the end of the part, which you can see on the image on the right, is used. This feature allows the part to be clamped and unclamped while keeping the correct form orientation. Aside from the lighter example, there are many different shapes in the injection mold industry that require out-of-round grinding. The video shows how the cylindrical grinding machine generates these forms. A high-accuracy C-axis, which is the rotation of the workhead, is used to interpolate the shape with the grinding wheel. Grinding these forms on this machine allows for the form and cylindrical features to be accurately positioned. The same wheel that is used to generate a form can be used to grind straight cylindrical parts. This gives the machine flexibility for many different features. The neck ring is another critical component in the PET bottle industry. The importance of this component is to create consistency in the injection molded container's neck. This component is also responsible for creating grooves and threads that are often associated with sealing the injection molded end product. When forming plastics, the neck ring accuracy can cause leaks or failures of the bottle. Additionally, this is the area that will receive the most torque when a consumer is closing or opening the containers. The following slides will show a number of different components to be ground, and they can also always be ground in the same machine configuration. So a machine that has flexibility is able to grind many different components in the mold industry. To process the neck ring, 2 setups are performed as well. In setup 1, the front shoulder is ground using an OD wheel, and the grooves on the ID are processed using an ID wheel. The second operation and setup are to grind the correct part thickness so that the location of the ID grooves are positioned correctly on the final product. Another example of a component in the mold industry is the lock ring. This is very important in the manufacturing of injected molding components because it ensures that the neck ring and the core pin come together in the proper orientation. The image at the bottom shows how the neck ring in blue and the core pin in purple look during the injection mold process. Being able to grind both tapered features in a single setup creates very accurate relationships to these components. The accuracy directly relates to the quality and consistency of the wall thickness for the injection molded parts. To assist in the manufacturing of lock rings, the cylindrical grinding machines can be equipped with a swiveling work table. Various machine models in the industry can offer swivel ranges beyond 90 degrees. The video shows the swiveling table to grind ID tapered surfaces. By swiveling the work table, the tapers can be programmed without using formed wheels or interpolation. This allows for an improved surface finish and added flexibility using a straight wheel that can be used in many different features. Here is a standard operation plan for the grinding of the lock ring. The first setup is used to grind the face for flatness and the ID on one end of the part. After the face is qualified, we can rotate the part and clamp against the chuck face. Operation 2 on the upper part of the operation plan is grinding the 2 surfaces where the neck ring and core pin make contact with the lock ring. Grinding these in a single setup ensures the relationships between the injection components, as I mentioned earlier. The mold cavity is the final component to this assembly. The forms shown above are used as blanks to create larger injection molded components. The cavity must have accurate forms to ensure that the wall thickness remains consistent for the final design of the container. Any thin spots will create a failure mode when the bottle or container is pressurized or filled. The cavity can be ground in a single setup using multiple wheels. The ID bore and spherical shape are generated using a single ID wheel. The 2 other wheels are used to grind the front taper and face to create accurate mating surfaces for the other components. To grind these features in a single setup, it is important to have multiple wheels. In the video, you can see a cylindrical grinding machine with 3 ID spindles and 1 OD spindle for grinding outer diameters, internal diameters, and faces in a single setup. The last 3 examples can all be ground on a single machine. Depending on the part volume, a single machine can be used to grind all the different components in the mold industry. As discussed with the out-of-round operation and interpolating Z-axis on the machine, thread cycles can be added similarly. Threads are produced by interpolating the Z-axis motion and the C-axis rotation in accordance with the thread pitch. The thread form is dressed into the wheel. With this method, small helix angles can be produced by manipulating the dress form into the wheel. For large helix requirements, an A-axis can be implemented on the machine. This is a rotational axis on the wheel itself, as shown in the two videos. The reciprocating screw neck ring, and other threaded components can utilize thread grinding on the cylindrical grinding machine. And that concludes my portion of the presentation. I think right now we're going to open it up for questions. If you have any that are typed in, we'll get started answering those.
That was excellent. Thanks so much. Now, before we begin the question and answer session, I want to remind you all that this webinar is being recorded, and you'll receive a follow-up email with a link so you can revisit the presentation whenever you'd like. Here's the first question for our panel. What tolerance are you holding on the PET bottle core pin example for combination turning/grinding?
I guess I'll handle that one by actually not answering it. We have a handful of customers that manufacture these parts, and we have some confidentiality agreements with them. So to mention tolerances at this point would not be very prudent. If you have examples or requirements that you're looking at, like bidding on or things like that, if you want to contact us, we can go over the part prints with you and discuss methods and tolerances and put quotations and cycle times together for you. But in this particular case, we really shouldn't discuss tolerances.
Of course. Next question. On an internal mold, can a radius be generated without a formed wheel?
Yes, there's a couple different ways of doing this. If it's an internal form, you can generate that using nose radius and contour grinding this feature. Also, there's many radius grinding machines available where the B-axis or the workhead actually swivels during grinding. So you can actually generate external or convex radius forms using the swiveling workhead. This is for OD and ID.
The next question regards a point that has been addressed about untrained operators. I have a lot of untrained operators. Do you offer courses on grinding basics?
Yeah, we offer courses at United Grinding for basic grinding technology, which would be from the basic work holding tooling to what different types of diamonds are available in the industry now, along with different types of abrasives. So it's a very basic, this is a grinding wheel, this is a grinding machine, and this is how you would process your parts. And then we continue to go further with that. We have classes, basic classes on running a Studer cylindrical grinding machine, and then we can get up into more advanced topics such as some G-code programming for some forms and shapes and things like that. So we do have those classes. There's a link on our website. So if you need some help, please let us know.
Sounds great. Next question. Can I grind a small taper angle in a bore with an out-of-round capability?
Yes, that is possible with our software. However, you cannot rotate a B-axis or swivel a table when you're generating this feature. The only possible way to do this is with an angled wheel. And so it really depends on the length of your taper that you're looking at to be able to grind this feature. It is not possible to rotate or swivel the workhead in this situation. But yes, it is possible with our form grinding cycles.
Okay, you mentioned software. We have someone who's curious about what is the software that you're using for grinding?
There's two different types on the Studer machine. There's the new version of Studer's basic operating system called Studer Win, which is mainly for our straight OD and ID machines. And then there's a Studer Sim software for our radius generating machines, and maybe Andrew can look a little more on that.
Yeah, we also have a software called Studer Sim on some of our internal grinders for generating forms. This software was built kind of for the mold and die industry, and it takes DXF files of your prints to generate your tool nose paths for internal contour grinding and radius grinding. So it's dedicated to that industry.
Another thing to mention too, since all the machines now are Windows-based controls, that's hence the name Studer Win for the software. Prior to that, we still do offer offline software programs, Studer Grind and Studer Technology, to name a few, or Studer High-Speed Machining, depending on the application you're doing, or Studer Thread, of course. You can do these on a PC and then input those right into your machine also. But since we went to the Windows-based control, we also offered these formerly offline programs integrated in the machine. So to do out of round, or to do thread, or to use the technology for setting the feeds and speeds based on material, wheel spec, and all that, it can be internal to the machine also.
I see. Our next question reads, over time, my ability to hold tolerances and cycle times on my machines degrades due to machine wear and tear. How do your machines hold up over many changeovers and setups?
Well, the Studer machine, with its unique weigh system and its base, hold up very, very well. We also offer some PM packages. We've got some discounts going on right now, but we offer programs where we can come in every 4, 6, 12, 18, or 24 months and do a PM on your machine and look for any issues it may be having.
The next question it reads, when do we decide to move from parallel axis thread grinding to an A-axis with form parallel thread grinding?
Typically, when the helix angle of the thread gets above 5 degrees, then it's just too difficult to try to put that form into a wheel, and that's why we would go up to an A-axis.
I see. Well, if no one has anything to add to that last question or any of the other topics that we've addressed,
Ross,
let's see.
I'm sorry, this is Doug Emerson here. We just got a quick question real quick in here I saw. It's asking if our in-process measuring is usable on other grinders. The answer real quick is no. It's because the software and the integration itself are tied into our internal or integrated into the control itself. It's not physically possible to mechanically take that gauging and put it on another machine.
I see. Well, thanks for expanding on that, and that's just great, gentlemen. Thanks for joining us today, and thanks to all of you in the audience as well. We hope you'll find this information valuable. If you have any other questions, or if you're viewing a recorded version of this webinar, feel free to